Okay, so we've defined our discriminator now. The next step is to define our generator. So let's get right to it. Having a look in our notebook here at what we've already done, we have loaded our dependencies. We have input our data. For me, those are apples. And we have defined our discriminator network. Now comes the time to define its great adversary, the forger, the generator network. Okay, so we're going to try to have the same kind of rough syntax here. So how did we do it up here? We defined, we should give this a little title here. Add a line above here to say that we are creating our discriminator network. And then so right below, we can nicely write a comment for whoever comes to read this later. So we create a generator network. We're going to define it in the same kind of way. So up here we said define discriminator builder. So here we'll say define generator builder. There's a few parameters for this generator builder. We have to define the dimensionality of our latent space. I found that the value 100 is pretty good here. So we'll have a 100-dimensional latent space to work with. The width, we're going to set that up with the same width as in our discriminator. So we set a kind of minimum convolutional network width of 64, so 64 filters. And I'm going to say 64 for the generator here as well. With the discriminator network, we exponentially increased the width of our convolutional layers, so 1, 2, 4, 8 multiples. So the general architecture of what we're going to do here, I'll give you a high-level overview before we start building it, is we're going to have the size of the image that's being generated slowly upsample, layer by layer, over the course of the generator's deconvolutional layers. So we're going to use a new type of layer, an upsampling layer, to increase that size layer to layer between the deconvolutional layers. At the same time, these deconvolutional layers are going to be taking features, they're going to represent features, and put those onto the image. As we go deeper into the generator, the number of features that we're going to consider in each deconvolutional layer is going to decrease exponentially. It's just the methodology that works here. So the final parameter, other than that width, is dropout. So we're going to set the same kind of dropout as we did for our discriminator. That's 40%. That's a hyperparameter that you can try to tune, but it certainly works fine. So just like the discriminator network, we're going to define our inputs first. How did we type that out? Define inputs, yep, exactly. And so the inputs here are going to be just the noise or latent space coordinates. So all we need to define is that it's going to be, the network needs to expect something of the dimensionality of our latent space, which we've defined as 100. And then we can define our first layer here. The way that we might typically build a convolutional network, where it starts with an image and then has convolutional layers culminating in a dense layer. So this generator is kind of the inverse. It's going to start with a dense layer and then turn into deconvolutional layers. So we're going to start with this first dense layer. I'm we can call it dense 1. It's going to have this 7 by 7 dimensionality. Eventually, by the time we get to the discriminator, the image size will be 28 by 28, thanks to upsampling several times, gradually making this image larger. We're saying here that we're going to have, in addition, the other parameter here in the dense layer. So this is, of course, dense layers are always flat. They're one-dimensional, but we wanted to have enough neurons to represent the 7 by 7 shape. And then the other element that we want to take into consideration here is to have this width of 64 neurons, filters, in the first deconvolutional layer. So that's why we're using the 7 by 7 by 64 multiplication here. We're going to use batch normalization a number of times through this network. And the reason why we use batch normalization is to maintain the mean and the variance of the parameters throughout the layers of our network. So if we don't use batch normalization, there's a risk that from when we randomly initialize our parameters, we know that when we use Glorot initialization, we're going to have a nice mean and standard deviation of our weights and biases of the parameters in our model. But there's a risk, if we don't use batch normalization, that these will shift, something called covariate shift, as we progress through the network. And with such a deep network, the generator feeding into the discriminator eventually is a part of our whole adversarial network, we want to use batch normalization here to keep everything in line. There's a batch normalization parameter called momentum, which is how much flexibility we're allowing the mean to have. And we're not giving it a lot of flexibility here. So this is all dense 1 stuff happening here. We have a few more layers. So we're also going to set our activation here to ReLU. Now recall that anytime previously in these live lessons or my other live lessons, the activation has simply been a parameter in whatever layer we're defining. So if we use dense or convolutional or what have you, I typically just define the activation as a parameter. Here, we're using activation as a layer. It's not a full layer in a sense, but it's kind of a sub-layer within this first dense layer. What we're doing here is we're being very particular about the order in which things are happening in each layer. So we're saying, I want batch normalization to happen before activation. I want to be sure that I have control over that. So we're taking an extra level of granularity here, specificity here, and part of why we're doing this is that generative adversarial networks are notoriously finicky, and so we want to make sure that we're doing everything correctly. After the activation layer, we're going to reshape these outputs from the one-dimensional dense layer into a three-dimensional shape for passing into our deconvolutional layer. So we'll use the reshape function here in Keras. And so now here you can see we had the 7 by 7 by 64 one-dimensional array for the dense network. Now, after batch normalization and activation, we reshape that into a three-dimensional 7 by 7 image with a depth of 64. So 64 possible filters of that 7 by 7 shape. The final thing that we're doing in this dense layer is adding dropout, which is simple and the same as we were doing before. Now come our deconvolutional layers finally. So we've talked about deconvolutional layers a few times. I've added an asterisk here because it's something we're talking about, we're building upon in this lesson. And this is also the kind of the main point here that I had in the generator. So now we're actually going to build those in the code. So let's call it conv1. And we're going to start by upsampling. So this upsampling part of the layer is going to take the 7 by 7 image and upsample it to make it just a little bit larger. And we're going to do this a number of times through the generator, as I've said a few times, so that we have this 28 by 28 by the time we get to the discriminator. And the reason why we're using 28 by 28, of course, is because the real images are 28 by 28. So we need to make sure that we're setting up this architecture in a way so that the real and fake images are the same size. So conv2D transpose, this is the actual name of the layer in Keras for doing a deconvolutional layer. So the transpose of a convolutional 2D, the inverse of a convolutional 2D, deconvolutional, two-dimensional, these are all synonyms for the same thing. Here we're going to define the number of neurons or filters in this layer. As I mentioned earlier when I started talking about this, this is going to exponentially decrease as we approach the discriminator. The shape of these deconvolutional layers throughout are going to be 5 by 5, which you'll notice is the same as the shape of the filters that we had defined in our discriminator for later on. We're setting padding equal to same, which is also what we did in our discriminator. And at this point, we're saying that our activation is going to be none, but we are going to set an activation after batch normalization. I'll show you. So again, this is us being really picky about the order in which things happen in this layer, pickier than ever before. So now we say, I'm going to do batch normalization, and we're going to have the same momentum as in the previous layer, 0.9. And now we're going to, as the last step in this layer, pass it through the ReLU activation function. So by doing it this way, by being so specific, we are enabling ourselves to ensure that the batch normalization is happening before the ReLU step. Okay, now we're going to do the same kind of thing a few more times. So we're going to have 3 of these deconvolutional layers. So let's copy the code for the first deconvolutional layer. We're going to rename it to conv2. And then we're going to change the input into the first part, the first layer of the conv2 layer to be the input from the output from conv1. And these guys are all going to be conv2 now. 2, 2, 2, 2, and 2. The parameters are largely the same as we add this additional layer, except that, as I've mentioned a couple of times, we're going to exponentially decrease the number of filters that are available. Number of filters, kernels, neurons, these are all synonyms again. All the other parameters are staying the same, so that's a relatively easy layer. And let's copy and paste that again for our third deconvolutional layer. So again, we need to change the naming to conv3, pass in conv2 instead of conv1. And in this instance, we're actually not going to upsample here. Otherwise, the size of our image would become too large. So we are, however, again, decreasing exponentially the number of filters or kernels or neurons in this layer. Kernel size stays the same. Passing in conv2, we're calling it conv3. We are going to have batch normalization with the same momentum again. And then the final part of the layer is the activation, the ReLU activation. That brings us to the end of our deconvolutional layers. And then for our final layer, it is a convolutional layer. And this convolutional layer has a single neuron. So the idea here is that we have a single image for each instance of noise that we pass through the generator. So we start with a whole bunch of different filters, a bunch of different aspects of the image, which as we move through the deconvolutional layer are pieced together until we get to this final output layer where we just have one neuron representing the one single state of the 28 by 28 pixel image that we are generating. The kernel size, again, is going to be 5. Padding is the same. And this time, activation is sigmoid. The reason why we're using sigmoid, again, is that sigmoid neurons output a value between 0 and 1, and we want this generator to be producing this one 28 by 28 pixel image with values at each pixel from 0 to 1 representing the darkness of the image, where 0 is white and 1 is black. So this corresponds to the real images. They're exactly that same kind of idea, 28 by 28 pixel images with a range from 0 to 1 representing pixel darkness. This layer is taking the COM3 as input, and the final steps here are to actually define our model. So just as in the discriminator, we defined our model this way, we're actually going to do it the same way in our generator. So we can copy and paste that code. It is indeed identical. And then we return that model out of the function. So let's create an instance of it. So here's our generator, a single instance created by generator builder. I made a typo here involving a capital letter. Of course, inputs here is singular. Let's try that again. And we're calling this width, not depth. Some people like to call that depth. I like the idea of width for my neuron layers. I like to think of depth as moving up and down through layers of the network, and width as the number of neurons or filters in the layer. But some people do call this depth. All right, let's try this one more time. So when we execute this generator builder function, it of course outputs all of the detail of all of the layers that we defined in the generator builder function. We end up with a total of 400,000 parameters, and that brings to a conclusion our creation of this generator part of the network. So we've defined the discriminator, we've defined the generator. Up next, we're going to tie them together into a single adversarial network, and we're going to learn how to train that as well.